I don't actually know if someone's supposed to introduce me, but I suppose I can introduce myself in a minute because I need to catch my breath. I just ran here from the shuttle. Okay, well, I guess I have your attention now. Is everybody ready to start? Because I think I am. Okay, good. I'll take that as a yes. So this is the talk on the kernel the kernel load day from 2 years ago. It was the one that was used in the quote Dugu attacks. But well, here let me introduce myself first. So I'm Julia, and I take things apart and figure out how they work. Here's what I'm going to talk about for the next 45 minutes. Basically, who, what, where, when, why, stuff like that. Things you need to know about TrueType fonts in order to understand the rest of the talk, and then the actual technical details of the bug. So I actually went through and counted up my slides. About 12% of them actually have words. 21% have pictures. And then about 67% are hex dumps. So, and they kind of go in this order. So, the beginning. So I was trying to figure out how to best represent a calendar or something, but I'm pretty sure this is self-explanatory. So so this particular exploit, the first confirmed sighting of it, Kaspersky found a sample of back in May of 2011, although there seems to be some indications that it may have been in use in 2010, or possibly as early as 2005, although I'm not certain about that anymore, because there's some other, there's an anachronism with the metadata, so I think it'd probably be at least 2006 for the absolute earliest. Either that or somebody changed the metadata around. I'll show you that in a moment. So anyway, it was actually discovered, or at least analyzed around August of 2011. Crisis, who are these Hungarian, I think, group. They originally discovered it, and then Semantic took their report and then wrote a much longer report out of their research. And then Kaspersky published a whole ton of stuff also. And if you go to Google, you can find them. So I'm not going to cover too much about the actual Dooku stuff. I'm just going to talk about this exploit here. So Microsoft officially named it in November, and started patching and so forth. And then also, curiously, this is about when I started looking at it, and while searching for information about it, I actually discovered that there was a Chinese website that actually had a copy of the exploit on it for a couple of days, and then it went away. And I don't know what the story was with that. And then it was fixed, and the patch was released at the beginning of December. And then not much happened for about 6 months. And then whoever it is who does the development for Black Hole apparently started testing this exploit, and at the time nobody actually realized it, or rather, I figured this out while searching for something else, and I found an email on the Snort emerging threats mailing list where somebody was like, "Hey, look at this thing. It doesn't work," and when I saw that, it was like I immediately recognized, oh, that's that. This exploit. So apparently, it was in testing on like some beta test site or something for the Black Hole exploit kit back in June, and then then it didn't really show up again until October when it actually worked. So this is when the big news was when it was released. Both the cool exploit kit and the Black Hole kit, which are actually kind of apparently actually the same, almost the same code base by the same author. So in a sense, so it makes sense that they both came out simultaneously because it's kind of the same thing. I think it is. I think this one, like they sell for more than that one, I think, was the reason why it's branded that way. So, and after that, basically everyone copied, because all of the exploit kits copy all the exploits out of every other exploit kit, there's very little actually new input into the system. It's just kind of copying and copying and copying. And you can if you actually sit down and like look at a bunch of exploits from a bunch of exploit kits, you can kind of watch over time as it's sort of like a like medieval. It reminds me of like medieval manuscripts, where like each scribe would occasionally introduce a small error, but over time you can essentially watch them build up in each copy of the parchment. So looking at a lot of exploits, you can see where you can kind of follow who copied from whom and what they messed up when they did the copy. And so actually later on I actually have a phylogenetic tree that is sort of based on that sort of logic. Anyway, so for Dooku, everything you want to know about Dooku is basically in this PDF that Symantec put out. So go and download this PDF from Symantec, and you'll know everything you want to know about the Dooku malware, but it won't actually tell you anything about the actual exploit, because this is pretty much all it says about the exploit. And they never actually released any details. There was no later version of this document. So I'm going to give you the details that aren't in this. So this is whatever. Anyway, I'm not going to talk about Dooku. Go read that document. go to Google, look at the wiki page for Dooku. It's all there. I'm going to talk about the part that's not in there. So anyway, so the initial, so they did actually say that the initial vector was a Microsoft Office Word document that had an embedded font in it, which exploited the font rendering engine in the Windows kernel, because the Windows kernel renders fonts in kernel space in ring 0 for drawing pictures, and it seems kind of insane, but it was I stumbled across this document on Microsoft's website that it was like written back in like '99 or like 2000 or something like that, and it was basically the entire document was a rationalization for why moving the GDI layer into the kernel was a good idea. And it's just hilarious reading this thing in hindsight. Anyway, it's basically, it says this sort of thing over and over and over again in different ways. And actually my favorite one is this one, where they claim that making this change won't affect the DoD C2 or E3 security certification. Anyway, go if you want to like laugh a bunch, go and read this document here. So anyway, so I was actually going to put the actual contents of this message here, but I didn't actually get a chance to cut and paste it in here. But this is the snort message where somebody's like, "Hey, what's this font exploit thing?" Anyway, that was back in June of 2012. Anyway, but so basically the evolution of this was the initial exploit that was used in the Dooku attack. This was in the Word document. It was an embedded OpenType font, okay. So let me explain that. Is everybody here familiar with the Microsoft Active Protection Program? Okay, so Microsoft. So before Patch Tuesday every month, Microsoft sends an advanced notice to a bunch of antivirus companies and IDS companies and so forth saying, hey, we're about to fix these vulnerabilities. Here's the information you need to know in order for you to detect them the day the patch goes out. And so basically, they send out advanced information on this. So and so that's why, like every time a new patch comes out for Windows, like SourceFire and McAfee and Symantec all say, "Oh, we detect this brand new thing." It's because they get advanced. They get the advanced information through map. Anyway, so the map version, I think it only actually got sent out in like November, although the metadata in it was from August. So the particular copy that was sent out was it apparently been reconstructed then, because it was converted from an embedded OpenType font into a regular TrueType font. In any case, the other thing is that it had the payload removed. There was an entire Windows kernel device driver in the middle of the font, which was loaded by the shellcode, and they zeroed all that out. And then all the shellcode, all the kernel shellcode, they zeroed all that out too. And they figured out, well, basically, and they figured out basically how to essentially get to the bug in the kernel so they could fix it, and how you go about to detect this. But they hadn't analyzed further, so they didn't notice that it actually left the actual important part of the exploit in, and it was actually still functioning because map doesn't send out actually working exploits except this time on accident. So in any case, so the Black Hat version. So I haven't actually seen the any information about. I haven't actually gotten any of the data for like the whatever broken version it was back in June. But looking at the current versions, basically the 32-bit version is almost bitwise identical to the map version, but different from the Dooku version. And then pretty much every other exploit kit is bitwise identical to this one, even with the same names. There was one exploit kit, I forget which one, where it changed the name of the font to ABCDEF instead of Dexter. But otherwise, it's identical too. I mean, it's like literally bitwise identical. Put the files next to each other, it's like every single bit is the same. Anyway, the other curious thing is there's this 64-bit version, and I don't know where that came from exactly. I mean, it looks like it's derived from the 32-bit version. I don't actually. These are all pretty close. It's hard to tell which direction the arrows go. But the 64-bit version is almost identical to the 32-bit version, but with a few other small changes, which I have on this slide. And yes, literally the metadata in the files is identical. All the font tables are identical, and they're the exact same places. All the jokes in the font are constant. I'll get to that. Whoever wrote this apparently spent a lot of time and put a lot of personal touches on the exploit. Everybody uses the identical 32-bit font program. Although the exploit kits, the first couple of bytes are nulled out, and it doesn't actually affect the execution of it, but I'm not sure why, if that was on purpose or, I mean, it doesn't really change things, but I don't know why it would be nulled out on purpose. Anyway, so so anyway, yeah, the only difference is the shellcode that was included in each of the exploits. Everybody puts their own thing in there because well, I'll explain how it works in a minute, but it's basically literally you can just drop your kernel shellcode in at a certain offset in the font, and it'll just magically run it. It's a very reliable exploit. And I'll explain how that works in the technical part. But in any case, the 64-bit version, it's slightly changed. Mostly some offsets were changed, and also the middle part of the exploit where it manipulates the global VM state. In the 32-bit version, it only makes one write into that structure, but in the 64-bit version, it makes about 16. And I haven't precisely figured out what they all are quite yet. But I'll go through the data here in a second. And then the shellcodes that were with them was the Dooku one. It basically loaded the device driver from within the font itself. It's conveniently mapped into the kernel by the time the shellcode runs. The funny thing about the shellcode, though, which is a particular type I've never actually seen anywhere else before, was it was written to actually work on both 32-bit and 64-bit kernels. It would just you could drop it on either system and it would execute correctly. It was actually really, really well written, and I have no idea who wrote it because I've never seen it on most other exploits that I've looked at. So anyway, the map one basically had everything nulled out. And then for the black box, it basically does the typical download exec back from the exploit toolkit website, and then run it and stuff like that. It's pretty much the standard download exec shellcode, except that it deals with like loading the APIs from like kernel32.dll instead of ntdll or whatever. And then some general bookkeeping. You don't actually have to deal with like the IO privilege level stuff though in the shellcode, because it ends up running in the context of the of win32k.sys anyway. Well, here I'll explain it in a minute. So, okay, back up a bit more introduction. So everybody here has heard of TrueType Fonts, right? Okay, who here has never heard of what a font is? Okay, so anyway, there were fonts. There were bitmaps, and then PostScript came along, but Adobe patented a bunch of the stuff. And so there's TrueType, which doesn't follow any of the Adobe patents, and so forth. It's basically for PostScript, you do the things like this. If it's a quadratic curve, there's another point in the middle. So you draw these out. You basically construct characters by drawing these outlines through a bunch of control points, and then you once you've drawn it, you then rasterize it and so forth. It's all pretty straightforward, except there's aliasing issues though. If as you get down to as your sample size approaches the size of your actual drawing of your characters, you end up getting dropouts. And it basically so when the font gets really small, it becomes completely unreadable. I mean, like, look at this. So Nyquist has some things to say about that. So the way that TrueType solves these avoids these sort of problems or solves these problems or whatever like that is that when the pixels get really big in relation to the character, when it's at a very small point size, it makes a bunch of the parts of the outline thicker so that it hits more pixels. And so this is like what it would be like when it was at like 72 points or something, and this would it be like at whatever that is, 10 points, and the thing is that the making fatter is like literally you have to write a program to do that, and so there's the information on how to like make things fatter and thinner is the point size changes is known as the control value table, and it looks kind of like this, and it looks like this stuff too. Actually, if you really want to know, you can go to Google and type in TrueType font spec, and Apple, Microsoft, and Adobe all have like huge sections of their website that they go into immense detail on like all of this stuff like that. So I'm not going to cover that, but you can see it work here because like between these 2 point sizes, you can see the thickness of the characters change, and up there too. And it's basically these points. It's these places where the control value table kicks in and starts making changes. So in order to do this, it's not like a linear thing. There's an actual Turing complete virtual machine language for doing the transforms on the character glyphs and the outlines. It's actually you can actually do a lot of transformation. You can actually make the so there's a what was it? There's a sort of a security issue with TrueType fonts in that you can you can write a font or program a font that draws different characters at different point sizes. So you can make text appear completely different, like on a screen versus on a printer, by just basically changing the font program to say, oh, substitute the letter B for the letter A when you're at this point size. Anyway, but anyways, that's the reason why TrueType fonts are actually programs. And if you're a TrueType program, pretty much your universe is basically a stack of operands, and then a storage area, which is an array, essentially. And then this control value table, which is also an array, basically. And then various global graphic state, if you if set some kind of symmetry for drawing or whatever, it'll be stored in that. So anyway, here's how to go about analyzing this. So TrueType fonts, the actual on-disk format's pretty simple. It's like the RSX11 style of, here's an index with offsets and sizes, and then that's it, basically. So it's the index is always the beginning, and then anything else can be anywhere you want in the file. There's just offsets there. So we're looking at an actual file. The first 16 bytes are the first 4 bytes are the magic number, and then the which there are actually several. Windows and Mac kind of. Anyway, it's nobody actually. Everybody wants to make their own standards and not follow anyone else's. So, you know how it goes. And then the next the next 16 bytes, 16 bits is the number of tables. There's 16 in this particular case. And then there's a bunch of stuff you don't really care about. TrueType fonts were like designed to so that you could use them on like on a computer with only like 128K of memory and running off of a floppy disk. There's a thing here for doing binary tree searches on it, but if you have like more than like a couple of kilobytes of memory, you probably don't really need that. I don't know if anyone actually uses that anymore, but anyways, so this is the part that is interesting, I guess. It's 16 of these. There's 16 of these. You can see there's a magic value for each of the tables. In this case, it's shifted over by 4, but imagine that these were wrapped around, if it helps you think about it. And the actual values are pretty straightforward. So like this one is the embedded bitmap data table. There's a checksum, which is basically all of the bytes added together. Nothing fancy. It's literally just the sum of all the bytes. And then the offset where you find it in the file, and then how long it is. Ta-da! The next one is the embedded bitmap location table, et cetera, and so forth. So for example, the font program, in this particular case, starts actually like on the slide. So it's about, was it 206 plus 12 bytes in, which is right there. And so this font program this is actual TrueType virtual machine opcodes, and they're pretty straightforward. Generally, each opcode is only 1 byte, and then some of them, mostly the push ones, have from 1 to 7 bytes of operand. So in this particular case, you can see it's a push, and it pushes that value on the stack. Then it pushes this value on the stack, and then multiplies them together. And then it pushes this other number on the stack. So the stack is like the product of these two, and now it has this thing on top of it. Then it adds those together, and then it sticks 12 on top of that, and then adds 12 to it. And I have no idea why it actually does this, actually. This program's not actually executed by the exploit at all. I have no idea why it's here, to tell you the truth. But in any case, that's how you read it, really. So the other weird thing is that the moment you actually look at this font in a hex stump, you'll immediately notice this giant block of Unicode in the middle, which is the name table, which is where the copyright information is usually kept. For this particular font, it says that the name of this font is Dexter Regular, copyright 2003 Showtime Inc. Nobody knows why it says this. There's no actual real font of this name. And I don't know, if you have any theories, let me know. So the odd thing about this, though, is I actually went and looked up, so Dexter's like a television show, which I've never seen, but I actually went and looked it up, and apparently the show didn't actually begin broadcasting until 2006. And so I don't know why it says 2003 there. It seems like an anachronism. And I don't know if this table is just here to confuse people or what. In any case, there's a bunch of that stuff in this font, actually. So, by the way, I'm using the actual exploit for the font example I've been going through so far. So, the other thing you'll probably want to know about it is you'll probably have to deal with are embedded OpenType fonts, which are basically most of the stuff from a TrueType font compressed with this proprietary compression scheme, which for some reason the W3C consortium decided to make part of the standard and stuff, and there's not really any tools to deal with it except I think Tavis or Mandy, I think it is, several years ago wrote a little utility to convert back and forth. It's full of bugs, so you'll have to go and fix it and have to ignore like a lot of seg faults and stuff like that, and it's undocumented. But it actually works. I've actually managed to get it's actually been very, very useful for like extracting data out of embedded OpenType fonts. Anyway, so let me catch my breath. Okay, I'm not speaking too quickly, am I? Okay. So I wanted to try and like pace myself because I know a lot of people here like English isn't your first language. So there's this kernel bug. Oh, did I mention? Yeah, there's a kernel bug. It's in the font rendering engine in the kernel, and since it's in the kernel, anything that uses fonts on Windows is vulnerable. So Internet Explorer, Office. It turns out actually Chrome and Firefox have their own engines, so they're not. But pretty much all of Microsoft stuff, it all uses the standard Microsoft GDI stuff. And pretty much if you embed this font in like a web page or an Office document or whatever, it will work. And it'll even work. It'll work even if you're running like Office in a sandbox, because the exploit doesn't happen in Office, it happens in the kernel. And also you don't have to deal with any privilege escalation because you're already in ring 0. So what the actual bug was, so all right, so one of the things with TrueType fonts is it also, besides outlines, it also has bitmap glyphs, and you can there's a set of numbers for like the X and Y offset for kerning two letters together. So if you take like these two letters and you want to stick them together like that, there's a variable that tells you what that number that gives you what that distance between those should be. It also works for vertically written languages as well. So there's both an X and Y offset. So the bug was on the Y offset. Basically there was so when you do this, it didn't actually check that the Y offset wasn't way past the end of the buffer, and so you could basically write a bitmap on top of something else in the kernel. But it was, since it's doing a bitmap merging operation, you can only add bits. You can't remove them. So you can set bits to 1, but you can't set bits to 0. so the question is like, what would be the best bits in the kernel to overwrite with ones in order to make an exploit? So here's the answer. Here's the exploit rather. So this is the actual copy. You basically control that number, and they're basically ORed together. So you can add bits, but you can't remove them. Yep. And actually, if you actually reverse the patch, you'll see that this was what was changed. This is the actual bug. It basically just takes these two numbers, multiplies them together, and then uses that as the offset without actually checking it's not past the end of the first buffer. In this particular, for the exploit, it was that 2,624 bytes past the beginning of the first buffer. I think that's right. And this is what it actually looks like in the file. So if you're writing a signature or something to detect this, you want to check that this value isn't like really big. That basically, you take that number, multiply it by 32, and that's your offset. And this is the bitmap that gets written into memory. It's a 1 pixel by 1 pixel bitmap with only the high bit set. So it's writing 1 bit into memory. I think I have a slide that says that. Okay, yeah. As a reminder, that's what it's doing. And so there's only actually 6 characters defined in this font. There's 2 characters. There's 4 characters that are just nulls. And in order to trigger the vulnerability, you need at least 2, because in order to trigger the vulnerability, you have to kern the 2 together. So for this particular exploit, the 2 characters were a colon and a closed parenthesis. And in order to trigger the exploit, you had to put them together in exactly that order, like this. See? That was the trigger for the exploit, or for the vulnerability. In any case, this is all zeros. Although it's actually, it's all zeros. Although I'm kind of curious about the stuff that's not zeros, why it's in there. I don't know if it's like leftover from earlier versions of this or something. Those are the other 4 characters. Anyway, so here's how the exploit actually works. I didn't really need to repeat this, but yeah. So how would you do this? Anyway, so basically, as you can see, there's only 1 bit that's getting added to memory by this exploit. And as it turns out, as luck would have it, there's the place where the person who wrote this exploit, the bit they chose to add was to the length of the CVT array, because as so basically it was 128 added to 1, which is the original value. So it now believes there's 129 entries in the CVT array, but there was only actually 1 actually really allocated there. And as luck happened to, as it just so happened to be, the CVT table happened to live immediately, like 4 bytes prior to the global VM state in memory. So this is a reminder. So way down here in memory is where the actual original bitmap was. It skipped all that and it wrote a bit there. I really didn't write a bit there. It wrote a bit here, and that made it think that this was actually this long. What this did was essentially make the whole global VM state accessible from within the VM itself, because you can now read and write to the global state through the CVT array. So the entire rest of the exploit is written in the TrueType virtual machine language. So the other things, there's actually if you're doing exploits, there's a bunch of really useful stuff in the global VM state, like for example function pointers, because if you look at some of the so this is from the documentation. off Apple's website. If you look at a bunch of the instructions for, like, say, rounding, for example, there's like whatever 6 or I guess 9 or something different rounding functions. You can either round up. You can round down to 0 or round up to the next number, or if it's like at halfway between, round in this direction, or if it's this, then you round in that way. And there's a bunch of things, but it's essentially you're setting a state for what the current rounding state is. So whenever you call the round instruction, it'll go and do the actual implementation for whatever the current state is. And so in the Windows kernel, the actual way this is implemented is with a bunch of function pointers. They basically just essentially have functions for each of the implementations for each of these, and then basically depending on the state, they just change a function pointer to which one is the current one when you call round. The one that was actually used in the exploit was this instruction right here, set single width, and that's also a function pointer. So backing up a bit, so back in November, I got this exploit dropped in my lap, and it was like, Julia, figure out what this thing's doing. Forget if we detect it. Actually, most of what I do is answering the question, hey, do we detect this? So I had to figure out if we detected this. But so I had the map version. So the map version, there should be another slide here with what it actually was. But I can tell you about the glyph program because this slide is right here now. So basically the shellcode was replaced with a call back to the current location. So it was an infinite loop that kept calling itself, and it would fill up the stack and then blue screen the box when you hit the end of the stack frame. And so if you set up Windows to dump your kernel when it crashes, you can then pull it back into KD, the kernel debugger, and see what broke or where. And so so when you do this, the last thing that was executing according to the stack frame was this execute glyph program. And so the glyph program takes this other TrueType font program and executes it. So it's 100. It's that long, and it's basically more of this kind of stuff. So when you bring this thing into KD, let's see. It tells you a bunch of stuff. This is the stack dump, and so it was an execute glyph program. And when you look at these are the registers when it died. If you notice, this was the shellcode here, which is essentially jumping back to itself continuously. If you look at the stack pointer, you can see it hit the end of that page of memory, and so forth. But there's all this other stuff. So anyway, if I don't know if you've, I'll go through this if you've not spent a lot of time doing kernel debugging. But these are the arguments to each of these functions. There's not actually a symbol for this one, actually, but so each of these, if you go look at there in memory, it's the font program, and the which is this stuff. That was what it was executing. So apparently it crashed in the middle of this font program. So this is other argument here. This is the second one. It's apparently pointing to that other random program in at the beginning of the font. So it was remember at the beginning when I was saying here's how you parse a TrueType font by hand. So it was that other one up here. Or no, sorry, it was this one. Anyway, but this is what it was doing. and so the it's this long. Well, if you go back and look, you can see it's basically it starts there and it goes there, and there's a bunch of flags. which occur after the glyph program, and they're not actually used for anything in this particular exploit. So I don't actually know why they were set to this value of 3137 in hexadecimal, because it doesn't make any sense interpreted as flags, but it doesn't make sense as like 3137 either, because it would have to be the other way around. And I don't know. If anyone has any guesses, let me know. All right, so going back to the crash dump, the last thing that was, the last instruction that was actually executed, or rather, the place where we were going to return to if it hadn't crashed was that instruction. It never actually reached this instruction, I should say. And my laser pointer ran out of batteries. So let's have to do this without a laser pointer. So actually these mics don't move now. So so somewhere down this panel, somewhere down that function leads to a crash, or rather, it leads to the shellcode execution, which this is basically a snapshot of the state when that happens. So that's just what I said just a second ago. And I don't actually have so normally there's presenter slides where you see what the next slide is, so you don't repeat yourself, but I'm not actually doing that, I just have a mirror display. So if I seem to be repeating myself, sorry about that. So anyway, the third argument is this mysterious thing here. These are obviously all pointers because they're all in that particular memory segment, and the index pointers are kind of pointing mostly near the end, but not all the way. So it was apparently doing something about here. So it turns out these are like which instruction it's currently on. And so the last instruction it actually executed with this SSW instruction, and then never actually got any further. So apparently it crashed on that one. And then, and then the stack is like full. So this is what the stack looks like. You can see it's returning, it would be returning to itself over and over again, but I don't know. So the other thing is sort of doing a quick guess that the jump into the shellcode is probably one of the registers plus an offset. Well, ESI is that plus that offset. So any place that ESI plus 50 hex appears, that might actually be the jump to the shellcode. Or EAX plus that many bytes, that might be it. Or EBX plus 4, that could be what the jump to the shellcode is, because somewhere there's a jump or a call that essentially leads into the shellcode execution. So anyway, at this point, basically you pull up IDA and then actually look at what's going on. So this is what it looks like. You pull it up in IDA, and one of the first things you'll notice actually is all this debugging. If you load the regular debugging symbols, there's like this list of functions here, which are exactly the same ones that are in the TrueType documentation. This one actually, if you go to Apple's website, and so it's basically these are all of the actual implementations for each of the opcodes, and they all basically look like this. This is the not operator. It does some stuff, and then it goes either this way or that way, and then here's like the negative negation operator, and this is not equal operator, and so forth. And they all basically look like this. And if you look at it for a bit, it's pretty clear that this branch is taken when there's an error, and that branch is taken when there's not an error. And so you can figure out, this is like multiply, so you can figure out, well, okay, that's going to be the error code. That's going to be where the error is stored. These are the inputs, so this is where the operands and so forth are pulled from and so forth, and etc. And it's pretty straightforward. It's basically just a big jump. There's a big jump table in the in Win32k.sys that basically you take the byte value for the opcode, multiply by 4, go to the jump table, jump to that, and execute it, or call that, or whatever. So the first thing every one of these functions does is it makes a copy of that into EAX. And I mean, like all of them. So I don't know if you've ever used IDA, but it's got this, like, a bunch of really useful things that, for just saying, hey, like, what functions actually like do this, touch this particular memory address. Anyway, so yeah, it's pretty safe to assume that whatever this is must be a global VM state, and these ones here, well, those are all error codes and so forth. You can pretty much, just kind of looking at it, you can like logically figure out what all this stuff does, even without the debugging symbols. Particularly because you'll notice certain variables are only used by like loop instructions, for example, or this one's only used by relative jumps, and so forth. So. And then this one's only for conditionals, etc. Okay, and then and so forth. There's also there's a debugging symbol called local GS, but there's no global GS. But it's probably safe. But well, there is actually a global GS in the name of this function, but it's not actually anywhere else. So it's probably safe to assume that there probably is actually such a thing that's just been stripped from the MSDN kernel debugging symbols. Anyway, so you spend a bunch of time doing this for a couple hours, and you figure it all out. And then so this is pretty much where we left off. So it crashed somewhere down that path, and this is the main execution loop, I believe. Yeah, so somewhere in here is a call or a jump that goes to the shellcode. And then this is the actual main loop. Okay, so basically the actual, here's this. Anyway, so that's the actual jump through the jump table for each of the opcodes. Like that. It's byte value of the opcode times 4. Go that far down and call that. So anyway, if you do all this stuff, anyway, it's not that hard. It's just kind of tedious. I tell people that reverse engineering is not actually. Oh no, I'm almost done. Hang on. Okay, hang on. Let me. Okay, I'll go through the last part really quick. I'm apparently running out of time. So you don't need to know about this actually. So. Skipping ahead, I'll get to the good part. So this is actually the structure. This is the interpreter, the base of the interpreter stack. This is the storage area array. This is the control value table, which is like the number of pixels, point size. When I crashed the kernel, I was only using a 4-point size. That's the CVT count, which is 129 now. It originally started off as 1, and then there's some other stuff. And so the important part is right there, because that was where the bit was overwritten by the bitmap, and so the CVT table. You notice it's like literally like right 4 bytes ahead of this, and so now this whole structure is now inside the CVT. So the other thing you need to know is. This Boolean right here is the autoflip Boolean. There's this pair of operators called flip on and flip off. If you go and look at them, you can see it's set to 1 or a 0 at that particular offset in the structure. And you go and you look at flip on and flip off and see what they do in the documentation. It's like, oh, they set this Boolean on and off. Anyway, so it's what it does. It's in the docs. And so there's also this pointer after the shellcode, which is basically the call to itself thing in this particular sample. And so the other funny thing is the name is different in the debugging symbols. This is SSW in the documentation, but LSW in the actual debugging kernel symbols anyway. So Anyway, so this is actually the implementation for that instruction, which remember was the last time there was the last opcode that was executed. And you do look down in the middle right here. It's right there. Yes. It basically grabs a function pointer out of that structure and then jumps to it. That one. So in this particular case, it's now currently pointing to the shellcode at the beginning there, as a reminder. So the way this works is you push some stuff in there. It's looping and it keeps track of the iterator in like the storage table as the first entry. Then it flips the flip-on bit off, so it's a 0 now. Remember? And then down here, it'll flip it back on. And in between these instructions, basically go and read the. You'll see these pair up a lot like that. If you're going to read, you'll push like a byte on the value, and then you read from it, and so forth. Goes and reads the first CVT value, which in this case was 0 because that was originally what it was, which is there. And then it flips the bit back and then checks to see if it changed. It reads the same value again, subtracts them, and if it changed, then it jumps over to this other branch here, but it didn't change this time, and so it goes and it loops. This is how you do a loop in TrueType assembly. And then it's actually weird. This is actually an undocumented thing. I actually had to like go and reverse the function to figure out. So the JROT thing is supposed to jump. It's true if it's greater than 0 or false if it's 0, but it's not defined for negative. But in this case, it's negative, and so I actually looked that up. I think it actually doesn't. It's considered false, actually, I think, in that. So anyway, there's also a funny bug here. This is actually should be whoever wrote this mixed up the decimal and hexadecimal version representation of 128 versus 80. This should actually be 80 hex, not 50 hex. I don't know. It doesn't actually affect the exploit because it basically works within the first 25 iterations anyway. So basically, it's flipping this bit on and off, and eventually, after you use about 37 times, you eventually actually find it. And so now you know where you are. You now know where you are in the structure. So it makes some copies of some of the data. It goes in basically reading a bunch of the function pointers out. The one right here, the first one is the okay. Oh, I'm almost there. Okay, so it does some stuff and does some more stuff, and then anyway, and so basically it's basically taking that number out of the array, adding which points to where the original font program was in the font. The shellcode is about 80 bytes past the beginning of that, so it basically gets that pointer, adds 80 to it, and then writes it back on top of the function pointer to the SSW instruction, and then it calls SSW, and that jumps into the shellcode. Ta-da! Okay. Like that. Okay. And then actually some other people have published stuff on this too. Google, and then also I found out after I wrote this that 2 other people had also actually written up stuff on it. So anyway, any questions?
Presentation online?
Let me think. I think it's only online as a video from either CCC or CanSec, which are earlier drafts of this, but it's. I should actually. I'm actually planning to write this up as a white paper because I think it'd actually work a lot better as a piece of paper you could stare at for a long time. Yes.
Did you share the annotated IDA type?
Possibly. It's not that interesting, but I could probably. And I have to figure out where I left it. It's on a VM somewhere, but I could probably do that. I didn't actually write a lot of stuff into the. So the question was if I could share the annotated IDA file, but it's not very annotated. But I mean, I can see what it is. The other question was if the slides were available anyplace, and I don't actually think they are. Actually, no, I think CanSec, the version I gave at CanSec, I believe is actually on the CanSec website. So yes, the slides are actually online somewhere. Question?
Do you think there are similar vulnerabilities with the way image files are handled by Windows?
Yes, actually. So the question is if there are similar vulnerabilities with image files in Windows, and actually, historically, I can actually think of several real examples. Because, well, I mean, there was the Windows metadata thing is kind of a special case, but like the icon file one from a few years ago, and then I remember there was like a bunch of like GIF and like, or GIF or whatever, JPEG ones from like 7 years ago or something like that. So, anyway, I think actually a bunch of those were actually done in user space though. Although the animated cursor one I think was actually in the kernel. All right, any other questions? I don't see any other hands. So, okay, I think that's it. All right.